Hi, and welcome to this video on shared references and mutability. Now this is something we've actually already seen before, but I just want to formalize the definition and just re-emphasize a few points about this. So the term shared reference is the concept of two variables referencing the same object in memory. In other words, pointing to the same object, having the same memory address. So for example, if we write a equals 10, then we can create a shared reference to this object in memory. So we have this object in memory at some memory address and a points to it. We can create another variable that points to the same memory address simply by writing b equals a. Just keep in mind, Python variables are memory references. So when we say b equals a, what we're actually saying is set the memory reference of b equal to the memory reference of a. That's what that assignment is doing. It's not copying values, it's copying memory address references. So b points to the same object in memory. Now the same thing really happens when we define, let's say, this code here. Let's say we've got a function, myfunc, which takes a parameter v. Now in our main code, suppose we write t equals 20, then t is a pointer to some object in memory. When we call myfunc t, we're passing the reference of t into this function. And so in its scope, it's going to have a variable v that will point to the same reference. We saw that in the last video. But that is another way of creating shared references. So shared references exist all the time in our code. We usually have functions and we pass arguments into them. So we end up with shared references. Now the following may surprise you. And again, we've seen that before. And we'll come back and take a look at exactly what's happening. But if we write a equals 10 and another line of code b equals 10, we might expect b to point to a different object in memory. It should be a different object. But in fact, what ends up happening is that b references the same object in memory. Python did that automatically for us. And the same thing if we look at a string, s1 equals hello, s2 equals hello, well, we end up with both s1 and s2 pointing to the same string. Again, Python's memory manager decides to automatically reuse these memory references. Well, we'll take a look at that very soon to see why that's happening. But the question here I want to answer is it even safe? And well, the answer is yes, because these objects are immutable. So even though a and b and s1 and s2 are both shared references, if we modify s2 or we modify b, the only way to modify the value that those variables are pointing to is by changing their memory address reference. And so by doing so, we would leave a and s1 alone. So yes, it's actually quite safe to do that, and Python actually uses that in order to do a few optimizations that we'll talk about when we get to Python optimizations. Now, when working with mutable objects, you have to be a little more careful, right? So let's say we create a shared reference. So a is a pointer to this object in memory, 1, 2, 3, the list at some memory address, and we set b equal to a. Again, remember, this creates a shared reference. So b points to the same object as a. Now we have to be careful, because if we modify b, let's say we append 100 to b, well, we're going to append 100 to this object here. That happens to be the same one that a is pointing to. So once we've modified the state of that object, well, then a has essentially as a value, as a developer we think of a as just a list, right? Then its value has changed as well. Why? Because it's pointing to the same object in memory. So with mutable objects, the Python memory manager will never create shared references, because that would not be safe to do. So if we write this, a equals 1, 2, 3 and b equals 1, 2, 3, then we are going to end up with two different objects in memory. So we'll have this list at some memory address, and b will point to a different list with a different memory address. The lists are equal, they're both 1, 2, 3, but they're not the same objects. Okay, so let's look at some code and let's just see in practice how this works. So let's start with setting up our own shared reference. So let's say we have a equals, and we'll use a string. Let's say hello. And then we'll set b equal to a. So now we can look at the ID of A. Maybe I'll use the hex version, hex of ID of A. It's this memory address. And if we look at the memory address of B, we'll find that we're actually pointing to the same memory address, right? So we set up a shared reference by setting B equal to A. Now, we know that Python does that automatically for us. If we say A equals hello and B equals hello, then we can look at the memory address of A and we can look at the memory address of B, and again we see that they are the same. Now, we didn't set up the shared reference. The Python Memory Manager did that. We'll revisit this in a few videos to see why it's doing that and when does it actually do this. It doesn't do that all the time. But the question that we asked was, is this safe to do? And yes, of course, because if we want to change B and let's say make B equal to hello world, right? Then if we look at the ID of B now, it has changed, right? It used to be this memory address right here, and now it is this memory address. It has changed. But the memory address of A, well, we didn't touch that, right? That stayed the original memory address, okay? So A is still hello, and B now is hello world. And that's because a string is immutable, so the only way to change the value of B, right, the perceived value of B, is by pointing B to a different string object, okay? Now, it's not quite the same when you're dealing with a mutable object. So let's use a list, which is a mutable object, and let's set a shared reference by setting B equal to A. Now, again, the memory address of A and the memory address of B are the same, right? As you can see, they're both the same memory address, which means, again, we have a shared reference. So if we say B append 100, then we're going to append 100 to that list, but it's a shared, it's a list that's shared between the variables A and B. Both A and B are pointing to the same list. So the memory addresses of A and B are still the same as before and still equal to each other, okay? And if we look at the contents of B, it's 1, 2, 3, 100, and A is going to be the same. So by modifying B, we modified A. And that, of course, also happens when you pass a list into a function, right? The function creates a shared reference to that list and can possibly modify your list outside, right? That you define outside of the function, but you passed into it. So you have to be careful when you're dealing with mutable objects, because everything in Python is passed by reference. And so you can get unintended side effects. You can also get intended side effects, is that if that's what your function wants to do. If you want to do an in-place sort maybe of the list, then this is great, right? Because you can do an in-place sort, you don't have to return it and reassign it. But you can also have unintended consequences. Okay, so lastly, one thing I want to look at very quickly is just this concept of this shared reference that Python does for us automatically, right? We looked at hex of ID of A, hex of ID of B had the same reference. Well, I just want to show you that if we do that with an integer, A equals 10, B equals 10, then we can look at the memory address of A, and we can look at the memory address of B. Okay, you can see that they're the same. So Python did this automatic shared reference for us. We'll revisit this, but one thing I want to point out here is that don't count on it. It doesn't always happen. Let's say we say A equals 500 and B equals 500. Then we can look at the memory address of A again, which is that, and the memory address of B, which is a different memory address, okay, 8910, 8A90. So it doesn't always do it, right? Sometimes it does, sometimes it doesn't. We'll find out very soon when it does and why it does so. All right, thanks for watching, and I'll see you in the next video.